Assalamu alaikum, guys. Uh, so today's our topic is SSB, single sideband modulation. Previously, so single sideband or SSB modulation. So previously we have already seen about DSB, double sideband modulation, right? So we have actually already covered both the coherent and non-coherent modulation and demodulation of DSB, double sideband suppressed carrier, in a previous topic. So this topic actually will cover the SSB, single sideband modulation. So for that, let us consider a message signal. So let's consider a message signal M. Let us consider a message signal MT. So that is a message signal. We actually considered it earlier also, and let MF is actually the Fourier transform of this message signal, right? This is the Fourier transform of this message signal MT. So we will actually use some of the modulation technique that is actually similar to our DSB, double sideband suppressed carrier. So how our message signal is actually baseband. So we can see how our baseband or MF, or how our MF actually looks like. So this is actually the MF, the Fourier transform of the message signal. Here, FM is the maximum frequency. So capital FM 2 minus FM. So for this case, for this message signal whose Fourier transform is actually M of F, have a bandwidth, have a bandwidth of FM. So have a one-sided bandwidth of FM. This is actually the one-sided bandwidth of this signal. Okay. So what is the modulated signal then? So modulated signal is xt. The modulated signal xt is nothing but mt cos 2 pi fc t. Okay, here fc is the carrier frequency, right? Carrier frequency. Now this is actually what? This is actually nothing but this is actually a double sideband suppressed carrier. So this is a double sideband or DSB modulated signal. So for our cases, we can convert it to Fourier transform. If we convert it to Fourier transform, then xt becomes xf and mt becomes mf. Here this was a multiplication, so Fourier transform make it a convolution, and we actually derived this portion earlier. So we know that would be half of the del f minus f c plus half del f plus fc, which will actually, if we solve this convolution, mf will be shifted to fc. So mf will be shifted to fc. Okay, half factor is also there, and mf is shifted to plus FC. So FC. We know it earlier from our previous solution of DSB. So how this equation would look like if we draw the spectrum of this. If we draw the spectrum of this, how it look like. So the spectrum would look like the spectrum would look like okay, the spectrum would look like this. So if this is the center frequency from here, so this is the FC, this is minus C. So this is actually FC, this is minus FC. So it would be look like this. Something like that. Okay. So this will be FC plus FM. This is FC minus FM. This will be minus FC plus FM. This will be minus FC minus FM. Okay. And this is actually the signal xt. This is for the signal xt, which is actually mt cos 2 pi fct, or signal of xf in frequency domain. This signal xf. Here we can see this is actually double sideband suppressed carrier. This is actually double sideband suppressed carrier. So SSB actually starts from generation of the DSB. Until you can generate a DSB, cannot have a SSB. Once ideally you have a generate a double sideband, then by filtering or other technique, you make it a single sideband. So now here, so here from here to here, this is actually the total passband bandwidth of this modulated signal. So which is actually from here to here, this is actually what? You see, FC plus FM minus FC will be FM, right? So this is actually an FM. So the bandwidth of this is twice FM, twice of FM, which is actually the passband bandwidth of modulated signal, of modulated or DSB modulated signal actually, signal which is actually twice FM. Twice FM. This actually, this scenario is also true for this negative part also. Actually, this portion is nothing but the image of this portion, right? Because this is the center frequency. So this is actually the negative part of the signal. This is the positive part of the signal. So we know, you know it from our previous explanations. Okay. Now here, in this case, this part, okay, in this case, this is actually the LSB, lower sideband. This portion is the lower sideband, or this portion is the lower sideband. Okay, and we actually seen it earlier, right? And other portion is the upper sideband, which is actually this one. Sorry, is actually the upper sideband. This part is actually this part is the upper sideband. One is the lower sideband, LSB, and one is the upper sideband, USB. So we can write it USB, upper sideband. Okay. So where is the LSB bandwidth actually? LSB lower sideband. So lower sideband, this part is the lower sideband. Eh? So this part is the lower sideband, which is actually this part also, the lower sideband. So from where it is the lower sideband? Lower sideband is lower sideband, lower sideband, which is actually nothing but what is the range of this lower sideband, which is actually for our case from here to here, like from here to here, right? So from FC minus FM to FC, the one, like one portion here, and this portion also, right? This portion, which is actually from minus FC to minus FC plus FM, means minus FC to FC minus FM, that portion actually. So the in combined, the lower sideband is this portion, which is actually this part, and this portion, which is actually this part. So this combinedly creates the upper sideband. So here we make it as a union, okay, for expression. Same thing, the USB upper sideband is nothing but other portion, right? So upper sideband is actually this part, okay. So upper sideband is from FC to FC plus FM, also this part, for example, this part, which is actually minus FC to minus FC minus FM. So if you want to know the whole upper sideband, so the both of them will be, both of this band will be in union. We can express it in this way. Now, because we know the lower sideband individually and upper sideband individually, we can actually draw. We actually draw the upper and lower sideband. For example, let us draw the upper and lower sideband separately. So if I draw it again, okay. Okay, so here will be one, here will be the another one, right? So what we want to say, we are drawing the LSB first, lower sideband. So which one is the lower one? You can see here. So this is the lower one, this portion and this portion. So let us draw this two portion here. We actually mark it here, so it will be here. Yeah. So let us draw the lower sideband. So this is the lower sideband. So this is the lower sideband. So this is the lower sideband, right? So if we mark from FC to FC minus FM, so if we mark FC to FC minus FM, and this is actually FC to minus FC to minus FC plus FM. This is actually our lower sideband. The opposite one will be the upper sideband, right? So if I draw it again, the other portion, so here will be the one, here will be the center frequency of FC and minus FC. Sorry, something happened. Okay. Okay, so sharing was stopped. Let's share again. Okay. So if I draw the upper one, sideband, actually this one, this one, kind of this one, okay, which will be FC plus Fm, which will be minus Fc, to minus Fc, sorry, minus Fc minus Fm. This portion is actually our upper sideband. So I have just drawn the spectrum of USB spectrum, LSB spectrum and USB spectrum. Okay. So now, because we now know the lower and upper sideband individually, we can actually choose for a SSB single sideband, which one, upper sideband or lower sideband to be passed. Okay. So in this case, for example, in both cases, the passband signal, is actually FM. Okay. So for upper LSB from here to here, the also for USB to here, here to here. These are the passband of the passband bandwidth of this. So this is actually the passband. So what is the passband? Passband bandwidth for LSB is, you see, FC minus FC minus this one is actually the FM. Also, the passband for passband bandwidth. Also for, so this is for the LSB, this is for USB. This is also FM. This is a single sideband, right? Individually, they are single sideband. Either they are LSB or either they are USB. But in both of them are separately called the SSB, single sideband, and have a passband bandwidth of FM. Okay, so this is actually FM, or this is actually FM. So we can see that previously for DSB system, our passband bandwidth was twice FM. For single sideband, either LSB or USB, the bandwidth is FM. So which is actually half of the bandwidth. So the passband bandwidth of both the LSB or USB is, so we can write, so we can write that passband bandwidth of both LSB and USB is FM, which is nothing but the half of the bandwidth of DSB, double sideband suppress carrier. So what we are seeing that by using SSB, we have a significant saving of bandwidth. Okay, so LSB or USB, which is actually nothing but the SSB, results in significant improvement or saving. Previously, we have to use twice FM bandwidth. Now we have to use half only FM bandwidth. Okay, saving of bandwidth. So now, which is actually the nothing but the improvement, which is if we use saving of the bandwidth. What does that mean? Saving of the bandwidth is nothing but the improvement of the spectral efficiency. So that is actually nothing but the improvement of spectral efficiency, or spectral bandwidth is better. Improvement of spectral efficiency of the system. So spectral, now we can see what is that mean actually. The spectral efficiency, it is nothing but, how the spectral efficiency is considered. Like we have a information by the bandwidth. by the bandwidth. For DSB, this bandwidth is higher. Higher the bandwidth, spectral efficiency is lower. Now, in single sideband, this bandwidth is lower. So lower bandwidth gives actually you higher spectral efficiency. Means you need low bandwidth, so your efficiency increases. If you need higher bandwidth, if spectral efficiency decreases, because you are trying to send the same information in DSB and in SSB. Both the cases, the information content is similar, but you are actually using less bandwidth in SSB, so your efficiency increased. Okay. So what we can say, how much this efficiency? So what? Okay. So from here we can summarize that spectral efficiency of FSB. So spectral efficiency of SSB is twice of the spectral efficiency of DSB, isn't it? DSB. So in single sideband, the spectral efficiency is double because it uses half of the bandwidth. Okay, that is a conclusion from this SSB. Means SSB single sideband actually much efficient because you are only transmitting one of the sideband, not both of the together. Here you have to transmit both of the sidebands together. So SSB is much actually double efficient of this DSB. Now, how to generate this SSB modulated signal? So this topic we will discuss how to or generation of SSB modulated signal. So we just found that SSB are good. Now how to generate them? So a common mechanism used for this generation is called frequency discrimination. The method is used is called frequency discrimination. Discrimination. This is the technique that will be used for either generating a single sideband or double sideband from the original DSB signal. Okay, this is actually other way is also called a filtering technique. Actually, in general, simple filtering technique. By filtering, either these upper sideband or lower sideband, you can actually, or we can extract one of the from the DSB, right? So it's actually nothing but means actually you initially you have a DSB signal, so then you do the filtering to filter one of the sidebands, so either LSB or USB upper sideband. Now by this filtering technique actually you can have one of the sidebands. Okay, for example, let me draw this picture again. This one of the either LSB or USB, either LSB. We actually see this technique applying for both of this, either LSB or USB. Okay, so let me draw it in LSB or USB. So this time I will actually draw it side by side, so to help you understand like both scenario simultaneously. So imagine this is actually our, so this is actually our say lower sideband, say this is actually our upper sideband. Okay, so I'm actually redrawing this two figure, this one and this one. Okay, let's draw the lower sideband. So lower sideband will be here. So this is actually our center frequency, and here will be the lower. It will be the lower. Okay. So let us draw the lower sideband. Okay. So this is actually our lower sideband. Here our center frequency. So this is actually our lower sideband. The lower sideband. Okay. So which actually have a FC and minus FC. So this is actually FC minus FM. This is minus FC plus FM in lower sideband. Okay. In upper sideband. So imagine this is a center. So here actually the okay. So in upper sideband, we'll actually draw it this way. We'll draw it this way. Okay, which is actually this is actually FC. This is actually minus FC. Sorry, this is minus FC. So this will be FC plus FM. This will be minus FC minus FM. This is how the lower and upper sideband. Actually, these are the both of the picture. I just draw it. This is the upper and lower sideband spectrum. We actually draw it here. Okay. Now, for example, you want to have a lower sideband. What you need to have a lower sideband, or if you want to extract. So you see here. Let me draw the other portion, even like other part. This was actually the other part. So this was actually the other part of this lower end. So this is actually for USB. This was the lower part. Okay, which actually we now if we want to have LSB lower sideband, what do we need? We need a low pass filter. Low pass filter. Okay, so if I have a low pass filter, then I can. So if I have a low pass filter of for example, okay, say if I have a low pass filter, so I have, let me draw it again. So this one, this signal, low sideband signal. So if I pass through a low pass filter, for example, if I pass through this signal through a low pass filter, which has a frequency from minus FC to FC, then I will actually pass this signal through this low pass filter, right? Or if I want to have this upper sideband, what will I have to do? I have to pass through or extract this through a high pass filter. So I have to use a high pass filter. So this is actually a high pass filter. You see this, and sorry, this will be a high pass filter. So this is actually a low pass filter. This is actually a high pass filter. So if I pass through my USB upper sideband through a high pass filter, or if I pass through my LSB lower sideband through a low pass filter, I will actually extract those portion of there, right? Okay. Now, if okay, so for high pass filter, imagine I am passing through it through a high pass filter. So what is the transfer function of this high pass filter? The transfer function of this high pass filter should be it should be 1 for the frequency greater than or equal to FC. You see, this is FC. this is minus fc actually. So if the transfer function of this low high pass filter is 1, you see here it is 1, for all the frequency greater than fc, all the frequency greater than fc, then otherwise in this portion, otherwise it's less than, like in this portion, like in this portion, it's 0. So if this is the transfer function, then this will be the transfer function of this high pass filter, where we can see what is the cutoff frequency. fc is the cutoff frequency here. So the cutoff frequency of this high pass filter is fc. Okay, this will be the opposite in low pass filter. So here you see this one, this is a ideal high pass filter, because we have a sharp cutoff. You see, this cutoff frequency is very sharp. This cutoff frequency is sharp, which is actually practically it don't have happen. So for upper sideband, so the transfer function of upper side band is nothing but what? This xf multiplied by this transfer function, which is actually h, this transfer function h high pass filter of f. So this will be the the output of this after the filter. Okay. So for this one, so what is the transfer function for this low pass filter? So low pass filter, you see in frequency domain, of course, here this value is 1, and then here or here is 0. So what we write, that its value is 1 when the frequency is less than fc, or 0 if it's higher than fc, right? In other values are f0. So here also the cutoff frequency is fc, sharp cutoff. You see, sharp cutoff. So also the cutoff is also frequency is also fc here. So we can write the transfer function of LSB, lower sideband f, is nothing but the x f, which is actually this one for lower side. Okay, what we can write, actually we can make a little bit trick here, so to make it clear, x, so we can say this is LSB, so we can say x LSB of f into x HL low pass filter of, here we could have write upper sideband to make it clear. Okay. Yes, good. So for both of the cases, there is the filter we are talking about, either low pass filter or high pass filter. They are actually ideal. So how this low pass filter or high pass filter or this mechanism will work? So for this case, for example, we have a signal MT, right, which actually mixed with a carrier equal to cos 2 pi fc t. Then we got xt signal, is it? So the message signal and the carrier, right? Message signal and the carrier. So the message signal and the carrier, they multiply to generate xt. Okay, to generate xt, which actually the message signal and the carrier, they multiply to generate xt. Then this signal here, what we find, this signal is nothing but the DSB. This is nothing but double side band. So you need to extract one of the either LSB or either USB. To do what? You have to pass through. So if you pass through a low pass filter, then you get the X of LSB. Okay, so here what kind of low pass filter is like this. You pass through a low pass filter, where you have a FC to minus FC range. Okay, so for USB is also different. So we actually separated. You see, these are two mechanisms side by side comparison. Okay, two mechanisms side by side comparison. That's what I'm trying to do now. So again, you have a empty signal, which actually mix up with your or cos 2 pi fct means your carrier. You got xt signal, which is actually your double sideband. Now you pass through a high pass filter, and then you got x of upper sideband USB. This signal, where the transfer function of this filter looks like this, where you have a FC and minus FC cutoff frequency, right? Okay, so we know how to generate, and so this is we call it this is our LSB generation. So this is actually our LSB generation, lower sideband generation mechanism, which is actually this one, and this is actually our upper sideband generation. So you see, to generate an upper or lower sideband, or in general SSB, you need either an low pass filter or a high pass filter. Okay, where the filter response is like this, right? Which is actually the filter response of this one. For this is the filter response of this one, or this one, pictorially this one. So actually we know how to generate one of the sidebands. Okay, now we see in both cases these are the ideal. So this is also an ideal low pass filter. This is also a ideal high pass filter. That is also a ideal low pass filter. Means actually in practice it's very difficult to design a filter with such sharp cutoff. We can see the cutoff is very sharp at that moment, right? Cutoff is very sharp. This is actually ideal. Practically, this is not a possible case. Practically, these don't happen. So what happened in practically? For example, if I draw a practical scenario for this case, let us draw a practical scenario for this low pass filter. So let me draw this figure again. Low pass filter. So imagine this is our low pass filter. This is for the high pass filter. Somewhere here is the, let's see, try to here is the FC, here is the minus FC. Okay, so here is the FC, here is the minus FC. Practically this is actually our low pass filter. I'm trying to draw this ideal low pass filter here. So this was actually our ideal low pass filter. Would look like having a very sharp cutoff. Okay, so here it has a unit value between or below FC. Now that will not happen. That will not happen. What will happen? That okay, it will be very close to 1, but when it falls down, the cutoff actually starts from here to here. So the cutoff starts from here to here, something like that. Okay, so this point is not midpoint. Let's say here is the midpoint to make it looks nice. So this actually the pass band, right? For this case, this is the pass band for this low pass filter. So pass band of this low pass filter. And you see here there is a transient happen between this and this one. Okay, this is actually, so this is the pass band, then this part is a stop band. Stop band, this portion where no signal is passing through. This portion is called the transition band. Transition band. Transition from pass band to stop band. Okay, so it's actually this portion. This portion is actually transition from, this is actually our pass band. This portion, like this portion, this portion, this portion, this portion, up to this portion. This is our pass band. And it's actually transition from the pass band, and here is actually stop band. So this actually transition from the pass band to stop band. That's actually trying to say. Okay. Okay. Now, for practical filter, there is a finite transition band. That's I'm saying there is a finite transition band. This. So what we are saying that for practical filter, practical filter have finite transition band. Transition band. This is actually true for the upper sideband also. Now, if this is the case, what happened to the signal? Where was the signal? We can actually, we'll draw it again. Okay. Let us draw this signal again. To see if instead of this ideal low pass filter, if the low pass filter response looks like this, like practical, this is a practical low pass filter instead of ideal low pass filter. What happened to this signal? What happened to this LSB? What happened to this LSB? So what we said earlier, that okay, imagine this is our like this one example. This is actually a DSB signal, double. This is actually our DSB, double sideband signal, where we have like both one. Now, if we pass through a low pass filter, you will actually have a one of the sideband actually this one. That's actually I'm trying to say. So if instead of ideal, if practical filter is used, actually, of course, when you use a filter, that will be definitely practical. How the shape looks like of your passband signal, passband or LSB. We are all taking as a LSB as a example. So here actually our this is actually our FC. This is actually our FC. So this is actually FC. This is minus FC. So if I draw the filter here, the practical filter, this is actually our practical filter look like this. This is for LSB. So I'm drawing this part, LSB, lower sideband. So here we can see FC is here. So let us draw in the same axis so it will be easier to understand. Okay. Let us. Okay. Where is the FC was here before? Here. Somewhere. Here is the FC. Here is the center. Here is the minus FC. Okay. Okay, now we are saying that our FC looks like this. Our FC. So this is LSB, lower sideband. So this is actually our lower sideband. So this is actually FC. This is actually our lower sideband. This is actually our lower sideband. Lower sideband. Okay. So our ideal low pass filter will look like this. So ideal low pass filter will be now instead of FC, so this is actually our DSB, like double sideband. This will be our DSB. So this will be cut off to the DSB. This will be cut off to this DSB. Which looks like similar. No. So it will be okay, yeah. Let me draw it nicely then. Now, so this is actually our DSB signal. Okay. Here actually the lower part. Here is the lower part. Here is the upper part, because this is our LSB signal. So if we have a double sideband signal, then if we pass through in a low pass filter having a practical response like this, our low pass filter practical. Then what will happen? Actually, in ideally, what it's supposed to be like this. In ideally, it's supposed to be like having a sharp cutoff, but it's not. Then what will be our filtered out filtered low pass filter will be look like this. So our this one, which is actually like this one. Then because of this one, because of this portion, we will have this signal. Right? We will have this here. Here is this portion is starts cutting. So here it will be like this. Same thing for this sideband, it will be like this, and at here it starts like this. So this is actually our lower sideband will look like in after passing through a practical filter. You see, here we can say, or we can see this portion, and actually there should be equal in both sides because of my drawing. It's not looks like similar. These two portions look similar. Okay, let me make a little bit correction here. Correction. So it will look like this. Something like that. So this portion is similar. So after practical filter, this actually supposed to be our LSB. This actually this two part. This part is actually LSB, which actually contains a little bit of frequency content from the higher part, which is actually this part. Because of this, response is not sharp or not a sharp cutoff. Okay, because of this, compared to the ideal. Sorry. So what I'm saying is, in practical filter, or by using a practical filter, the double sideband, only a portion of the signal, this portion of the signal or this portion of the signal will be filtered, including a portion from the higher frequency because of the lagging of the sharp in practical low pass filter, sharp cutoff in a practical low pass filter. So we can have an extra portion actually included with the LSB, which supposed not to be within, which supposed not to be with a, in a LSB, but because of the use of the practical low pass filter, this portion comes. Okay, so parts of the, so what we can say, you see here I am already drawing it for the LSB. I'm not drawing this picture for USB, which will be the same for both the cases. So the parts of the band, so we can see the part of band, which is actually greater than FC. You see, this is FC, eh? So this portion, and this is minus FC, which is actually this portion, and minus FC that actually contained with this LSB, with the LSB, which is supposed not to be there, but because of this use of a practical filter, they are there. This extra part, this part, and this part, they are called vestigial. They are called vestigial. So a whole new modulation technique actually arises from this vestigial. We call it vestigial sideband modulation. Sideband modulation, and will be discussed in one of the next lecture. So what we can see here, that if we have a, what we can see there, if we have a double sideband suppressed carrier signal, then by filtering we can have one of the LSB or USB by using a filter technique, either using a low pass filter or either use a high pass filter. So this is the example of ideal, and if we use a practical low pass or practical high pass filter, then we see we can see, in addition to passing that lower LSB, a extra portion of the signal from the higher part or other part connection to this actually also included in this LSB. That portion is called vestigial, and based on this vestigial, a new kind of modulation also possible, which is called vestigial sideband modulation. So here ends our lecture for today.